Welcome to the fifth episode of the FORCESPRO demo series on active suspension control. In this video, we will show how to run the code for generating the FORCESPRO QP Fast solver for active vehicle suspension control. We are still in the active suspension control folder, but now focusing on the active suspension control QP Fast script used for generating the QP Fast solver. Similar to the previous video, we load the model data, model the road bump, and simulate the passive model. The main differences arise once we get to the MPC setup. Here, we want to show how to run the MPC problem for active suspension control using the QP Fast solver. For simplicity, the active suspension controller in this example will not be using the full preview information. The MPC setup has been slightly modified compared to the previous video. Here, we run the getCodeGenerationData function that generates the multi-stage struct for the MPC problem without preview. We can then generate the solver code for the QP general solver. Note that, even though we are trying to obtain the QP Fast solver, we still need to generate the QP general solver first, in order to obtain the cache problem data. This data will then be used to auto-tune the parameters of the QP Fast solver. Once the QP general solver has been generated, we run the simulation and obtain the cache data. The simulation script is implemented in a similar fashion to the one shown in the previous videos. Now, we can turn our attention towards the QP Fast solver. Using the class Forces AutoTune Options, we specify the tuning options for the autotuner. We also set all 4 actuators for the validation of the control output. Finally, we can generate, download, and compile our custom multi-stage QP Fast solver using FORCESPRO by running the ForcesGenerate QP Fast solver function. Note that all of the arguments have already been generated by the getCodeGenerationData function, besides the tuning options obtained via the autotuner. We can now rerun the simulation with the QP Fast solver and plot and compare the results from both solvers. Let us now run the script and see how the auto-tuning looks in real time. First, the QP general solver for solving the MPC without preview has been generated and downloaded. We can now collect the generated problem data and use it for auto-tuning the QP Fast solver. The auto-tune has now been completed and the tune solver has been validated. We can see that the failure rate is 0 and that the average deviation in the objective and control input is very small, that is, below the threshold set by the user. Finally, we can now proceed with generating and downloading the custom-tuned FORCESPRO QP Fast solver. By looking at the control performance of the 2 solvers, we can conclude that the control accuracy remains unaffected, given by the identical roll, pitch, and heave acceleration for both solvers. However, in terms of computation time, we can notice that the QP Fast solver achieves a substantial speedup of 4x compared to the QP general solver, making it a more suitable option for this type of control application. This completes the code example of this demo for the FORCESPRO QP Fast solver.